Hello. In this video we're going to be looking at combining resistors where there's a mixture of things in series, things in parallel, and figuring out the equivalent resistance and what's going on with the potential, current, and power through each element. So to do so, let's review Kirchhoffs Laws, which govern how circuits operate. First law is basically a statement on the conservation of charge, specifically current, and there are two main applications here. One, at any junction, the total current flowing in must equal the total current flowing out, and this is basically saying you can't have charges build up or disappear arbitrarily in the circuit. And when this is applied to circuit elements in series or along the same path, the current has to be the same for all of those circuit elements. When we look at the energy side of things, for any closed loop, the sum of the voltages gained must equal the sum of the voltages lost. Or you may see this written as, for any closed loop, the sum of the voltages is equal to 0. But again, whatever energy gain you gain in the circuit has to be lost in that loop. And when this is applied to circuit elements in parallel or along the same path, the potential is the same. So let's go over what series and parallel mean in a little bit more detail. So when we say circuit elements are in series, they're along the same path. Meaning that if you go through one, you have to go through the second one, you have to go to the third one, just like what we have here on the picture on the right. It's not that they all have to be in a straight line, you just have to go through all of them if you're following that path. And consequently, the current through each of them is the same. And if you're looking at combining resistors in this way, the equivalent resistance is just the sum of the individual resistances, and consequently, adding resistors in series is going to increase the circuit's overall resistance. But where it gets trickier is when we look at circuit elements in parallel. And when we say parallel, we don't mean geometrically in parallel. We mean that they're along alternate paths that have the same starting and ending point. So you can see on the figure on the right, there's nothing geometrically parallel about it, but you can go from the top point to the bottom point through the three paths, each with a single resistance. You can go through the left path, you can go through the center path, you can go through the right path. And whatever path you take only has one single resistor. And they all will experience the same voltage or potential drop. A way you can think about this is like you're going down a mountain. It doesn't matter which road you take when you go from the top of the mountain to the bottom of the mountain. It's the same change in elevation. This is what's happening here. There's different paths to go from the top to the bottom, but they all have the same starting and ending point, so they have the same change in elevation, so to speak. But the important thing is when you look at them being in parallel, there's only one resistor on each of the paths. Otherwise, you have to further subdivide the things. But when you have just a single resistor along each separate path, the equivalent resistance you gain by adding the inverses of the resistors. And the consequence of this is when you add resistors in parallel, it ends up decreasing the overall resistance of the circuit. This is because you're opening more options for the current to flow. So the way that you'll go about solving resistor problems when you have a mixture of things that are in series and parallel, like most physics problems, you have to break it down into smaller pieces. And what you'll do is look for resistors that are either purely in series or purely in parallel without any ambiguity. Again, when they're in series, that means the current flowing through one resistor must flow through the next resistor. And when they're in parallel, it means that they have alternate paths to go from one point to another point, and each path has only one resistor in it. What you'll do is you'll look for the resistance of just those pieces of the circuit, redraw the circuit with the replacement resistor, and then you just keep going through this process as many times as you need until you end up with things that are just purely in series or purely in parallel with the source. So let's take a look at an example here where we have a mixture of resistors in series and in parallel. And so what we want to do is look for things that are purely in series or purely in parallel. And if we look at following the path of the current, say from the voltage source, so we go from the voltage source, then we go to R1, then the current can branch off. And it could go from here down, go over here, or it can go through here. And so if I'm looking at going from this top location down to this bottom location, there are options available, so that means I'm dealing with things in parallel. And if I go through this branch, it's just a single resistor. If I go through this branch, it's just a single resistor. And I go through the far right branch, it's still a single resistor. So that means these three resistors are in parallel because I have three alternate paths going on, each with a single equivalent resistance. So what I'll do is look at just finding the equivalent resistance for just these three things in parallel. And so the way you do that is by adding their inverses. So 1 over this piecewise equivalent resistance would be 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor. In this case, we have a 2 kilo ohm, 5 kilo ohm, and 10 kilo ohm. Add them all up. You get 1 over RA is 0.8 and units of 1 over kilo ohms. And so we have to flip it around to get the actual resistance, which would be 1.25 kilo ohms. So we add the inverses and then we flip it over to get the actual equivalent resistance. So what we'll do is we'll take that equivalent resistance of just those pieces and redraw the original circuit. So let's do that. So all that business on the right side, I've now replaced with a single equivalent resistance, RA, that has a value of 1.25 kilo ohms. So all that business on the right can be replaced with that single equivalent resistance. Now when I look at the circuit, everything is just along the same loop. So R1, RA, and the source, they're all in series. So the equivalent resistance of R1 and RA would be the overall equivalent resistance of the source. And since they're in series or along the same path, I can just straight up add their resistances, and I get my overall equivalent resistance of the circuit is 5 kilo ohms. But let's look at what we do now if we want to get the current, voltage, and power for each resistor. And to get the equivalent resistance, it's almost like we work from the outside in. We're going to retrace our steps here. We'll start with the voltage source, and then we'll go through each of the redraws of the circuit, and for each redraw, we'll apply our series and parallel rules. If we have resistors in series, that means they all have the same current, and once we have that current, we can then solve for the potential. Likewise, if we're dealing with things that are in parallel, we'll start with the potential, the voltage, which is the same, and then use that to get the current. And the nice thing is we have a way to check our work at the end, and that is the power coming from the source has to be distributed through all of the resistors regardless of their arrangement. So the power of the source has to equal the power of the first resistor plus the power of the second resistor plus the power of the third resistor and so forth, regardless of how they're arranged. So let's do this for our sample circuit. We'll start with the most recent redraw and just care about our source. So we solve for the equivalent resistance being 5 kilo ohms. And we have the voltage of the source. We can use Ohm's law, V is equal to IR, to get the current through the source, which would be that voltage over the equivalent resistance. 40 volts over 5 kilo ohms would give you 8 milliamps for the current through the source. And the power is current times voltage, so 8 milliamps times 40 volts would be 320 milliwatts. So that's what's going on with the source. This is our most recent redraw, so we'll look at what's going on with R1 and RA next. So these things are all in series, they're all along the same path, so they all have the same current of 8 milliamps. So we have the current, let's get the voltage through 1, be its current times resistance. 8 milliamps times its resistance, 3.75 kilo ohms would give you 30 volts. And power would be its current times voltage. 8 milliamps times 30 volts would be 240 milliwatts. And then when we look at the voltage through A, its current times its resistance, 8 milliamps times 1.75 kilo ohms, which would be 10 volts. But it turns out we didn't even really need to do that math, because if we know we have 40 volts coming from the source and 30 volts being lost around from R1, the remaining 10 volts has to be lost across RA, because the sum of the voltages gained has to be the sum of the voltages lost through each resistor along that closed loop. So if I gain 40 and I lose 30, I have to lose the remaining 10 through here. So that's what's going on with these. Then we back it up to the last redraw, which was how we formed RA. And we formed RA by looking at R2, R3, and R4, each being in parallel. And since these things are in parallel, to form RA, they all have to have the same voltage of 10 volts. And so since we have the voltage, we can solve for the current through each of them by doing Ohm's law. V is equal to IR, so I is equal to V over R. And you can do that for each resistor and also get their powers. And what you should find is that if we have 8 milliamps coming in, that 8 milliamps is going to be distributed along the three paths, because sum of the currents in has to equal the sum of the currents going out. And sure enough, we have 8 milliamps coming in. It's distributed to 5, 2, and 1 for the three paths. Last step, we can check our work by looking at our powers. So we have the power of the source is 320 milliwatts, and I put down the value for the powers on each resistor, and sure enough, add them up, you get the same power for the source. So that's a good way to check to make sure everything was done correctly when you solve for the equivalent resistance and the voltage and current through each piece. So let's go through our steps again, how we manage this. When you have a mixture of resistors, some in series, some in parallel, you have to break it down, look for pieces that are purely in series or purely in parallel without any ambiguity. Series means they're along the same path. You go through one, you have to go through the other. When you have resistors that are purely in parallel, that means you have alternate paths going from one point to the other, and each path only contains one single resistor. If it's more than one, it's a mixture of stuff. So you look for paths that only have one resistor in there. That means that they're in parallel. If there's otherwise, you need to break it down even further. What you do is you solve for the equivalent resistance of just those pieces of the circuit, redraw the circuit with that replacement, and you just keep on going through this process as many times as it takes. Then when you want to figure out what's going on through each circuit element, you start with the voltage source. You know the equivalent resistance, so you can get the current through the source. Then you work your way through each redraw of the circuit. If things are in series, they have the same current. If you know the current, you can get the voltage. If they're in parallel, you know the voltage, you can then solve for the current. And again, at the end of the day, you can check your work to see if the power from the source equals the sum of the power for each resistor.